Assalamualaikum and good evening. Today we are going to present about a mini PET bottle recycler for additive manufacturing. So together with me is Ahmad Shafi Aiman, Ahmad Zulsafwat Ilhami, Noh and Halimatul Atika. So in this presentation we will talk about introduction, problem statement, project objective, IR 4.0, SWOT analysis, questionnaire, methodology, IR 4.0, elements, market and sales strategy, economic justification and expected outcome. So the problem is PET mineral water bottle are major contributor to global plastic pollution, and the gap for 3D printing is growing but relies on expensive non-recycled commercial filament. So for the current limitation is existing recycle system are typically large scale or very expensive for individual use. So the solution that we come up with is a compact, affordable, smart recycler to turn used bottle into 3D printing filament.
Hi, Assalamualaikum. My name is Muhammad Shafi Aiman bin Muhammad Zainizan. So now I will present the project objective. There are three main objectives of this project. First is to design and build a mini PET bottles recycling machine that converts used plastic bottles into 3D printing filament. Second is to promote sustainability through the reuse of PET materials for additive manufacturing. And the last is to test and compare the performance of recycled PET with commercial filament.
Hi, my name is Halimatul Atika binti Kamari, and right now I'm going to present you Industry for Integration, which consists research of contemporary technologies. Our project incorporates several industries, which cyber-physical systems, industrial Internet of Things, IIoT, and also additive manufacturing. For CPS, we have integrating an Arduino to digitally control physical heating and motor cooling process. For IIoT, we're using thermometers and diameter sensors to collect real-time data for quality control. And lastly, for additive manufacturing, we provide a decentralized on-demand material source for our 3D printing. On the next slide, I will present to you our SWOT analysis on our project. Our SWOT analysis consists of 4 items, which strength, weaknesses, opportunities, and threats. Strength, we have low-cost material and unique smart monitoring features. On our weaknesses, we require manual bottle preparation and potential for diameter variations. Next, for our opportunities, we have high demand in schools and hobbyist communities, which will push for a circular economy. Lastly, we threats on competition from established industrial manufacturers and also expected on falling commercial prices.
So now for the questionnaire, we have 4 sections. So for the first section is section A about requirements, features and performance. Among 16 respondents is 75% consent. Primarily hobbies and small business owner is 68.8%. Age 18 to 44 is 15% is use 3D printer and 25% is interested. And the next section is section B about smart or IR 4.0 plus price. Despite currently selling is 68.8% or discarding is 62.5%. PET bottles is 75% of respondents show high interest in recycling them into filament. The primary drivers is 56.3% each for these are waste reduction, business utility and DIY project. So next, section C is about respondent profile. High interest in recycling is 75% is driven equally by environmental, business and DIY needs is 56.3% each. User prioritize shredding and auto pulling features is 16.8% each, with an even preference for 1.75mm and 2.85mm diameters is 37.5% each. Safety is 16.8% and cost 56.3% remain the primary concern. And the last section is section D about problem and interest. Despite selling is 16.8% or discarding 62.5% PET bottles, 75% of respondents show high interest in recycling them for waste reduction, business or DIY needs is 56.3% each. Key prioritized include shredding and auto pulling features is 16.8% each, along with smart automation 75%, safety is 16.8% and cost 56.3%. The top concern, though 21.3% are willing to pay over 1,200 ringgit for the machine.
Okay, for methodology and workflow for phase 1, material preparation and PET feedstock processing, which is cleaning, drying and shredding bottles into uniform PET flakes and ready for extrusion. Output of phase 1 is clean and dry PET flakes for ready extrusion. And for phase 2, for machine design and fabrication, CAD modeling and assembly of the extrusion systems, which is from PET flakes into the hopper and feed into the heated barrel and going through screw feed into the nozzle, and then out of the nozzle through cooling, and lastly will be pulling and then spooling. These are the output of phase 2 for fully assembled prototype recycling machine. And for phase 3, which is system testing and commissioning, functional checks of motors, heaters, safety and feeding mechanism, which is part of the phase 3. Machine operates safely and is ready for parameter testing. And for phase 4, processing parameter optimization through extrusion trials. Multiple extrusion trials through experimental procedure and resource resource data will be recorded. Okay, for the phase 5, filament evaluation and quality testing, adjusting the temperature to stabilize filament diameter, quality inspection and handling check. These are the output of phase 5, which is tensile test sample preparation are all included. And for phase 6, which is 3D printing validation test, printer compatibility test, 3D printing test specimen to evaluate layer adhesion and finish. These are the output of phase 6, which is confirmation whether recycled filament is usable for additive manufacturing. For data analysis method, measurements are used to find the settings that give stable extrusion, consistent diameter and good print quality. And for final deliverables, the project concludes with a working prototype and CAD drawings, optimized extrusion settings, validated filament quality results, and a discussion of limitation with suggestion for future improvements. Okay, for the next slide, IR 4.0 elements. For IR 4.0 pillar, which is Industrial Internet of Things, IIoT, project application are sensors monitor temperature and filament diameter in real time. For cyber physical system, CPS, a microcontroller automatically controls heating and motor speed based on the sensor data. For additive manufacturing, recycled PET is converted into 3D printing filament for on-demand manufacturing. And for big data analytics, collected data can be stored and analyzed to improve filament quality. And for system integration, recycling and 3D printing are combined into one continuous process. And lastly, for sustainability, support circular economy by turning plastic waste into useful products. Next slide.
So now for the market and sales strategy. For the market, we will targeting a hobbyist, small 3D printing businesses, educational institution. And the approach for this is direct engagement. So we will demonstrate at a maker fair and university workshop. And next approach is sustainability branding, appealing to eco-conscious consumer by promoting a circular economy. So the value is 1.75 mm filament with real-time quality monitoring. By implementing this project, we will reduce the material cost and environmental impact. And for the production model is on demand and localized, where the commercial filament is global supply and by shipping. And for the IR 4.0 integration, we will be using a sensor and smart monitoring, where the commercial filament is standardized mass production. And like I said earlier, our target user is a institution, hobbyists and small businesses, where the commercial filament is focusing on mass market, industrial and professional.
Now I will explain about the economic distribution for our project. For the economic aspect, our project focus mainly on cost efficiency and long-term benefit. First, if you look at the commercial 3D printing filament, the price usually range about 25 ringgit to 99 ringgit per kilogram. So for the student or small business, this cost can become quite expensive over time. However, with our mini PET bottle recycle, the raw material cost is basically zero because we use waste PET bottle that are usually thrown away or sold at very low value. This means that after the initial investment, user can achieve almost 100 reduction in raw material cost for filament production. The estimated total cost for our prototype is about 1,960 cents, which is one-time investment. After that, user can continuously produce filament for their own without buying commercial filament repeatedly. In addition, based on market trends, the global recycled filament market is projected to reach USD 3.69 billion by 2033. This shows that there is a strong future demand for sustainable and recycled filament solution, making our project economically relevant and scalable. So overall, our project is not only environmentally friendly, but also financial, practical and sustainable in the long terms. So the next slide is for expected outcome and conclusion for our project. First, we aim to produce a functional prototype that works as a localized, small-scale PET recycle system. This means user can recycle PET bottle and produce 3D printing filament on site without relying on large industrial recycle facilities. Second, in terms of environmental impact, this project helps reduce plastic waste by applying decentralized manufacturing instead of plastic bottle ending up in landfill that are converted into useful product supporting the circular economy as a concept. Third, from an educational perspective, this project can serve as a reference for future research in sustainability manufacturing, Industry 4.0 application and additive manufacturing. It is especially useful for students, school and university. So to conclude, our project proved that Industry 4.0 tools such as sensor, automation and data monitoring can make high quality and sustainable 3D printing more accessible and affordable. It successfully combined technology, sustainability and economic value into one practical solution. So that's all from me. Thank you.